All right, here we go. So, first of all, welcome. For those of you who don't know me, I'm Mr. Oya. We're charging into another year. I know it's going to be a little different, but I know it's going to be good. We'll get to know each other, and this is going to go just fine. Don't panic. It's all going to be good. So we're going to jump into a little bit of math today, but first things first, I want to just get through some first day business as well. So let's just go through a couple items. Online assignments. So we're having some issues. I spent a lot of time preparing to have my stuff on Moodle, which is, I don't know if you're familiar with that, but it's something that you may or may not have heard about my Moodle before. I've in the past always done all of my Algebra 2 on Moodle. I've actually got the biggest math Moodle in the world. But I just found out here fairly recently that the district is no longer supporting Moodle. So here at the last minute, I found out that all my thousands and thousands of questions and my whole curriculum I've developed is not going to be available through our district. There was a possibility I was going to be able to push some of that into Canvas, but it didn't work. And now we're scrambling, and I think we're going to end up having a Moodle that we can access, which will be very good for you guys. I'll just show you a little bit how that works. Like if just a very brief demonstration here, kind of show off what Moodle looks like. In Moodle, all of the questions that I've written, not all, but most of them have the availability of giving you some feedback too. It's really handy because in Moodle, I can build in, for example, the Desmos graphing calculators that you're going to access throughout the year. The Moodle questions, every time you open up a question, you get a different question. Here's an example from later in the year. This is not math that we've talked about yet. So if the math seems a little bit over your head right now, it should be. We haven't talked about this stuff. But here's a question where I give you a graph of a parabola and I want you to write the function in vertex form. I want you to notice something here. I'm really hoping we can get back to using this stuff. And here's why. If I input a wrong answer, look what it does. It takes a second. But if I input a wrong answer, it tells me it's wrong, but it doesn't just tell me it's wrong, it shows me how to do it. Right? It gives you a detailed solution to that problem that goes through step by step, the kinds of steps that we're going to talk about in class when we get to this topic. It even includes some graphs that help you understand it, and it shows you how to get the correct answer. Okay? So I really am going to try my hardest and do everything I can to get us back into an environment where you guys can be working in Moodle like this. In addition to just the benefits, the math benefits, it does some other things that if I can make this happen, you're really going to appreciate. For one thing, it allows me to be much more relaxed about due dates, and it allows me to give you additional retakes on tests. So there's a lot of real powerful benefits. Once again, we'll see if we can get back to having access to that, but for now, we don't. So for now, we're just going to be using Google Forms for our assignments. And I know that's, it's not great, but it's better than nothing. And like I say, I think we'll move on to better stuff in the near future. Okay, so notebooks and class notes. Everyone should have picked up a stapled copy of all the class notes, right? And that we'll go through. We'll start that today. Start that process today. Those are also available through your Google Classroom. I'll have those as PDFs that you can just download and print out if you need to. So if you ever lose them or something, they'll be there. Notebooks. Now I realize that we're in distance learning here for the foreseeable future, and so I'm not going to be seeing you in class. If we were meeting in class, I would require notebooks and probably do notebook checks. But even though we're doing distance learning and you're outside of school, let me just give you an argument for why this is a good idea. I would like everybody to have a dedicated Algebra 2 notebook. Ideally, it should be one that's got graph paper in it because we do so much graphing. Like a spiral-bound graph notebook is perfect. This is where I would like you to do all of your homework. Okay, every time you do an assignment, I'd like you to do your work in the notebook, and here's why. Because when you have questions, the very best way for you to get your questions answered is just to take a screenshot of your notebook on the page where you're doing your work. Take a screenshot of that, or just hold it up to the camera and I can take a screenshot of that. And when I see it, it allows me to see the problem that you're struggling with. But even more than that, this might sound a little bit creepy, but for a math teacher, when I can look at a student's work, it gives me a glimpse inside their brains. I can see how you're approaching the problem. And a lot of times it allows me to very quickly figure out, oh, I see where your misconception is. Here's the part that you're doing wrong. I can see it in your work, and I can be very specific, and I can give you good, detailed information about how to fix the problem and how you can understand that concept better. So the notebooks are really crucial. So get a notebook as soon as possible. Item 3, attendance. Well, you're all here, which is great. If you do have to miss a day, it's not the end of the world. I will make high-quality recordings of everything that we do. I'm recording this session right now, in fact. Those will be available. We'll talk about how you access the videos in a little bit. But they're there. It's as an alternative to being in class. It's not terrible. But being in class is always going to be a better alternative than just watching the video. How come? Somebody tell me. Why is it better to be here than just watch the video? Somebody click on your mic and help me out. Or you can just type it in the chat if you want to. That's fine. We can do it that way too. There you go. Bingo. You can ask questions. It's so crucial when you're learning this stuff. And a lot of times questions they're just simple things. I can address them very quickly, but it helps. It helps if you just don't understand something I was saying. Maybe I was garbled when I said it and you didn't hear what I said, but let's get it fixed, right away. Ask a quick question. I guarantee if you've got a question, don't be shy, because there are at least 4 or 5 other people in the class that have that exact same question that are just maybe too shy to ask. So please be bold. Ask questions when you have them. The classroom Google Meet procedure, you did it today, so you're probably fine. What I will do between classes every day, I'm going to go in and start up a new Meet session for the next period. And I have to be the first one into the session in order for me to be able to present my board like this. So I'll always go in first and start it, and then I'll make the link visible. So typically, like a minute or two before class starts, you'll see that link open up. I've got to record my videos between classes as well, and there's a lot for me to do between classes. So it's possible on rare occasions that I might even be a minute or two late. But just hang in there. I promise you I'm going to be here. If it's the time for class to start and you haven't seen the link yet, it's coming real soon. And if it doesn't happen for more than a minute or two, then just send me a quick email and tell me something's wrong. Office hours. Here's how you do office hours. So if I pull this class over, let's see, where is this class? Here we are. Okay, so here's my Google Classroom. When you pop into the Google Classroom, you go to the stream page first. Really, the most important thing there is going to be that Meet link code that you can go to class using. Otherwise, this isn't a very important page. Every once in a while, I'll send out some kind of a message to people that might be important, but typically where you're going to want to go is to the classwork tab. That's where all the action is in the classwork tab. So this is where we're going to have some course information and resources that will be available. The way I'm going to structure the work is we're just going to go week by week, and typically what will happen is I'm going to give you the notes, and then there will be some assignments underneath that. So for example, if you click on the 1.1 notes, what you're going to see is just this stuff that I handed out to you, right? There's a PDF. Everyone should have that in front of them right now anyway, right? That's the handout that I gave you guys when you picked up all your materials. The assignments will be there as well. For now, they're just going to be Google Forms. So if I click on this, it's just going to take me into a Google form. And I'll always have the due date there. When you click on that, you'll see what the due date is. Another place you can always go, I'm going to be very good about this and organized. If you go to the Google Calendar for this class, you will see that I've got, I'm going to have due dates. Everything for the class, there will be a due date associated with it. It'll show up on the calendar. So if I click on this, it tells me that the 1.1 e-ticket is due tomorrow at, what does it say this here? Oh, it's supposed to say this is due at 1 p.m. tomorrow, so I'll fix that. Okay, and then typically I'll even maybe put a little link in here, so if you want to If you want to go in and just click on the link, it'll take you right to that e-ticket, right to the assignment. But I'm going to do and if I'm forgetting stuff, email me right away and I'll get it on there. All the important dates should show up on your Google Calendar, okay? What else? The syllabus. How do you get to the office hours? Sorry, I forgot that. So the way you get to the office hours, and why is that not showing up on yours? Okay, I'll fix this today after class. I'm going to go to a different class for just a second. So you'll see my period 2 class, for example. Okay, there'll be a little link under the course information and resources, and I promise you it'll be there shortly for your class. If you click on that, what you're going to see is a Google Doc. This Google Doc, it says Mr. Roya Math Help. I'm going to change this every day, so when you click on that, right before 1:15, a new link is going to show up, and if you just go to that link, it'll take you to my office hour Google Meet session. I'm just going to do one session that starts at 1:15 and ends at 3:30, and people can just drop in whenever they need help. It'll be just kind of like advisory was in the past. Does that make sense? So once again, you're just going to go to the resource that says Mr. Roya's office hours, open up the Google Doc and click the link, and that's how you get there. Okay, and then syllabus. I'm not going to spend a lot of time on that. The syllabus will just be in the course information section of the class. I don't want to spend a lot of time on this. The important thing for you probably to know is that for this level of class at Pendleton High School, the practice is 25% of your grade and the assessments are 75%. The way that's going to be broken down has already changed a little bit, so I'll change the syllabus to reflect this. But I don't think we're going to do, I'm just not sure about this yet. I don't know if we're going to do short daily questions. I think we're just going to do e-tickets and homework assignments. I might throw in some of these quick little questions, but really it's going to be broken down into 2 parts. E-tickets are short assignments that are due the next day. Homework assignments are a little bit longer assignments that typically have a little bit longer deadline on them. Like, for example, our first homework assignment may not be due until the start of class next Monday. Okay. I will tell you, though, with the homework, you definitely want to get it done as soon as possible so you can get your questions answered. It is a killer in a math class to get behind on that homework train. Once you get behind the snowball on that, it just rolls you over. You got to stay on top of the homework and things will go well for you. What else? Assessments are 75% of the grade. We'll come back and once we kind of figure out if we're going to have Moodle or not, we'll come back and talk more about the syllabus stuff. But for now, that's probably good. Okay, and then the last thing is accessing videos. We don't have any videos yet, but after today we will. I'll give you 2 methods for that. I'm going to give you access to a folder in your Google Classroom, and I'll just dump the videos in there so you can access them that way. The other thing I'm going to do is I have a educational YouTube channel, and I will create playlists on the YouTube channel, and I'll give you a link to that as well. So whichever way works best for you. If you want to just access them through your Google Classroom, or you want to just subscribe to the YouTube channel and get them that way, I don't care. Either way. They'll be available both ways, though. I will take videos of obviously the instructional sessions, but I'll even try to take videos of the office hours, and I'll just edit out the parts where nobody's in the meet session. But if people don't mind, if they're comfortable with this, I'll go ahead and record those. So if people want to go back and take a look through the questions that were asked, they might have the same questions. Okay? Questions so far? Does that all make sense? Give me a thumbs up. Good. All right. Perfect. Okay, so let's jump into a little bit of math then. So for today, we're not going to do much. I just want to do a little review of some concepts from Algebra 1 and maybe even a little bit from middle school. Okay, so all the numbers that you have ever seen, let me do one thing I can see here, it might be useful. All the numbers that you have ever used in your entire life fall under the category of real numbers. There are some other kinds of numbers that you've never seen yet. We will see them this year. For example, There are some numbers that are called imaginary numbers that we won't get to for a while, but they are different. They're different than the numbers you've ever used. Everything you've ever used up to this point, though, would be considered a real number. All we want to do today is we want to look at some ways that we can explore the set of real numbers and divide them up into categories that makes it easier for us to be more specific about the numbers that we're using. Real numbers can always be broken down into two categories: rational numbers and irrational numbers. And all real numbers are one of those two things. They're either rational numbers or irrational numbers. There's no other kind of real number. It's one of those two categories. So let's do just a little bit of review. Can anybody tell me what the definition of a rational number is? Now, I'm going to give you a big hint. The name sort of gives it away. The name rational number includes the word ratio, which is an important word in math. What's another name for ratio? You can either type it in the chat or say it out loud. Go ahead, Anna. Fraction, perfect. A ratio is just another name for a fraction. And so that gives it away. Rational numbers are all real numbers. That can be written as what? Written as what? Rational numbers are all numbers that can be written as fractions. Yeah, there you go. So, for example, rational numbers would be things like 1/2 or negative 2/3 or 4. How is 4 a fraction? What's on the bottom of the number 4? 1. There we go. Yeah, we could write it. We don't choose to because it's unnecessary, but if we wanted to, we could put a 1 on the bottom and write it as a fraction. What about, well, we'll look at other examples later. Okay, so those are rational numbers, anything that can be written as a fraction. So if all real numbers are either rational numbers or irrational numbers, and rational numbers are the numbers that can be written as fractions, what do you think the definition of an irrational number is?
A number that can't be written as a fraction.
Good. So those are all the numbers that can not be written as fractions. So what would that be? What's an example of an irrational number there? Can somebody tell me an example of a number that cannot be written as a fraction? Pi. There it is. I heard pi. Pi is one, right? Any other ones? There is. Yeah, there's one called e. That's good. E is kind of like pi. It's the natural number. 2.7128, something like that. It goes on and on. What else? Good. Perfect. Square roots. Yeah, some square roots. Like what if I picked the square root of 2? 1.4142, blah, blah, blah. It goes on and on and on, right? So irrational numbers are the numbers that cannot be written as fractions. Now, I want to take a second here, and I gave some definitions, and I want to just focus on this for just a second. I don't want to spend too much time on this, but I want to gradually throughout the year, I want to get you used to math notation, and there's a reason for that. Math is a very specific kind of language, and the language of math is purposely kind of boring and dry. The whole point is that we want to be able to communicate information in math that's unambiguous, meaning that it's not open to interpretation. You can't interpret it in multiple ways. Now, it's unfortunate that we're not all sitting in class because the first day I typically do kind of a fun example, but I'll describe this to you at least. Do you guys remember playing telephone back in grade school? Remembers that game? Right? So when you play telephone in my class, we'd start at one side of the room and I'd whisper some little bizarre phrase or sentence to a person, and then they're just going to, the rules, as you might remember, You're just going to pass it from person to person, secretly pass it from person to person. And by the time it gets to the other side of the room, what always ends up happening? It sounds completely different. I mean, it's crazy how much it changes from one side of the room to the other side of the room. And so that's kind of fun. We do that, and we start off with something. It ends up being some crazy different sentence than we started with. But then we repeat that with a math sentence. Something like x squared equals 9. And do you think that changes very much when it goes from one side of the room to the other side of the room? What do you think? You're right. I see people shaking heads. You're right. It doesn't. Typically, it doesn't change much, if at all. And part of that is because math is so boring. At least I shouldn't say that. Math is not at all boring, but the language of math is meant to be pretty boring and straightforward. It doesn't change very much. That illustrates why math is the way it is. Now, English, we talk about language other than math. It's meant to be expressive and emotional and colorful, and it's you can, just by changing the inflection of your voice, you can completely change the meaning of a sentence. It could be either sarcastic or serious, just depending on how you use your voice. Math is not that way. Math doesn't have that kind of freedom. It is meant to mean one thing and one thing only. So here's an example of math language. We said that rational numbers, and this is a good definition, it's all numbers that can be written as fractions. Well, here's how we would say that in math notation. Just a couple things I'm going to point out. And not that you're supposed to be experts with this. We're just going to gradually kind of work our way through this stuff as the year progresses. First thing we see are these brackets, these script brackets like that. Whenever you see that, that's what we call set notation. So in math, we would say rational numbers are a set. They're the set of m divided by n. Well, what are those? M divided by n. When you see this little bar, that means such that or where. Whoops. So rational numbers are the set of m divided by n such that or where m and n are integers and n cannot equal 0. Okay, well, we haven't talked about integers yet, but we're going to talk about that today. So we'll come back to this definition at the end, and we'll see if this all makes sense. But this is our mathematical way of saying all the stuff that's written in purple up there. Okay? Down here at the bottom, irrational numbers. Okay, here's the math definition of irrational numbers. It's the set of h where h is not a rational number. So every possible value of h where h is not rational, that would mean all of the irrational numbers. Everything that's not rational is irrational. Okay, one other thing I want to cover here, and that's the decimal part of this. Rational numbers as decimals. There's two things that can happen when I write a rational number as a decimal. What's one of them? If I write a rational number as a decimal, what's one thing that could happen with that decimal? Let me give you an example. What if we have something like, for example, 1/2? What is 1/2 as a decimal? 0.5. That's it, right? It stops after 0.5. Agreed? Just 0.5, end of story. Well, what do we call that? Yeah. Okay, so either the decimal terminates, where it's just it's done. It stops and it doesn't need to go on any further. Or what's the other thing that could happen? Like, for example, if I did 2/3, that's 0.66666 on forever, right? I could write that as 0.6 what? What's that line mean over the top? Repeating. Yeah. So when we take a rational number and we write it as a decimal, one of two things happens. Either it terminates or it repeats. Some other examples of repeating decimals. What if I did something like, what about this one? What if I did 0.183? which part is repeating forever in that decimal? Is it 183, 183, 183? What's the part that's repeating? If I just wrote that forever and ever, what would it look like? 0.18. Yeah, the 3 is the part that's repeating because that's the part that's underneath the bar, right? Or if I did something like 1.243 repeating, well then everybody see that's going to be 1.243, 243, 243, and so on, right? Okay, so when we write repeating decimals, we always put bars over the top that indicate that they are repeating. Okay, so if rational numbers as decimals either repeat or terminate, then what can you tell me about irrational numbers as decimals? What do they look like? If I take an irrational number like pi and I write it as a decimal, what happens? Yeah, they don't repeat and they don't terminate. They neither repeat nor terminate. So for example, does anybody know what a good decimal representation of pi is? 3 point what? 1. Usually 1416, maybe it's, I only know it to 5 places. A lot of people know it a lot further than that, but 14159, and then I'm going to put 3 dots after it, which just means it's forever. It just goes on and on and on. There's no pattern. Okay, what's the most accurate way to write pi? The symbol. Yeah, pi is exactly equal to pi. That's what that means. When I write the symbol pi, it means that whole exact number. It goes out. You know, we've taken pi out to trillions or quadrillions of decimal places, and it never repeats and never terminates. But what's the point? Any decimal that I write, any decimal representation of pi is not completely accurate because I have to stop at some point. If I'm going to write a decimal, I can't write it out forever because there's not enough time in the universe for that to happen. I'm going to have to at some point just say, okay, I stop. And then it becomes a rounded number. It's not exact anymore, right? Okay, moving on. So let's look at some examples here. Actually, not quite yet. We said that we can break real numbers down into rational numbers and irrational numbers. Well, the rational number part of it, the rational numbers can be further broken down. We could even be more specific, right? So for example, rational numbers are all the numbers that can be written as fractions. Well, integers, we could say that's a special class of rational numbers where the denominator is 1. Any fraction that can be written with a 1 on the bottom is an integer. All these numbers here, for example, like -2 is really the same thing as -2/1. We don't write the 1 on the bottom. It's not necessary, but it could be there, right? So the set of integers is a subset of the set of rational numbers. It sits inside of the set of rational numbers. A good way to think about the set of integers is if you think about a number line. You've been used to number lines for a long time. We've dealt with number lines in math classes. They typically look like this, don't they? 0, 1, 2, 3, and so on. Going to the left, I'd get -1, -2, -3, and so on. Well, the integers are just the hash marks on the number line, right? Okay, so how big is the set of rational numbers? How many rational numbers are there in the universe? Sure. Everybody agree? There's no limit to the number of rational numbers. It's an infinite set. Okay. How big is the set of integers? How many integers are there on the number line? Somebody else help me out here. You can just type it in the chat if you want to. That's fine. Okay, I'm seeing it. Infinite. Good. Okay, the set of integers is infinite also. There are an infinite number of integers and there are an infinite number of rational numbers. Which set is bigger? Or are they the same size because they're both infinite? Okay, the same, I'm seeing the same. Makes sense, doesn't it? Because they're both infinite. Boy, that sure seems like that should be the answer, but it's not. The set of rational numbers is infinitely bigger than the set of integers, even though they're both infinite. How come? Can anybody tell me why? It's a true story, by the way. The set of rational numbers is infinitely bigger than the set of integers, and yet they're both infinite. Crazy concept. Ah, okay, good. And here's the key. Because the set of integers is a subset, and that's an important word, right? A subset is a smaller set that's inside of a set. The set of integers is a subset of the set of rational numbers. All integers are rational numbers, but there are some other numbers that are rational numbers that are not integers. For example, like 1/2 or 5/3, right? Or we could do negative the square root of 2. Right? Those are examples of numbers that cannot be written as fractions. And so in addition to containing all of the integers, the set of rational numbers contains an infinite number of these other numbers that fit in between the integers, right? So rational numbers is infinite. Here's a smaller subset that's still infinite. Well, we could even go a little bit further than that. We could be more descriptive. If we say an integer, we're talking about any number that sits on a hash mark on the number line. What if we restrict that just a little bit more? What if we restrict that and we're only going to look at, for example, maybe we're going to eliminate the negative integers, and we're just left with 0, 1, 2, 3, 4, 5, 6 forever, right? Well, that's what we call the set of whole numbers. The set of whole numbers has a lowest value. It starts at 0. Whoops, what's going on here? Oop. It has a lowest value, but then it just goes up forever from there, right? And if we extend this a little bit further, if we eliminate some more integers, if we eliminate 0, we're only left with the positive integers. Well, that's the same thing as saying the natural numbers. So the natural numbers start at 1 and just go up forever. Okay, why do we do that? It's not that big a deal, honestly. We just do that so we can be more specific. A lot of times we like to talk about the smallest set that a number sits in. Like if I were to say, for example, the number 3, what's the smallest set that the number 3 is included in? Well, it's included in rational numbers, but we can get smaller, right? It's an integer, but we can even get smaller than that. It's a whole number, but even smaller than that, it's a natural number. So 3, the smallest set that it belongs to is the set of natural numbers. Okay? Questions? Give me thumbs up, thumbs down, sort of middling on that one. Okay, good, good, good. All right. You remember talking about this stuff in the past? I know I'm going slow, but I want to ease you into things today. It's first day back at school, so we're going to take things kind of easy today. So identifying rational numbers, there's not a lot going on here. All this is really talking about here is just any number that can be written as a fraction, I can turn it into a decimal. How would you do that? Probably on a calculator, right? You're probably just going to enter these on a calculator and look at the decimal equivalents. So what would happen if I put in -5/7? If I went out far enough on my calculator, I would see that the packet of numbers that starts to repeat is that whole thing, 714,285. I'd get negative 0.714285, 714,285, and so on and so on. So I'll write it with a repeating decimal bar. 15 over 5 reduces to 3. So that's obviously a rational number because it's an integer, right? There's a 1 on the bottom. And then 13/25, that becomes a terminating decimal. Okay, and that's what we would see in our calculator. Okay. What about these? Let's just take these one at a time. You tell me, are these numbers rational or irrational? And if they are rational, let's write them as a decimal. So what about the square root of 25? Rational or irrational? It's rational. Yeah, it's a square root, so it's kind of tricky, right? Because like the square root of 2 is irrational. But what can we do with the square root of 25? How can we simplify that? What is the square root of 25 equal to? 5. Okay, so that process of going from there to there is what we call simplifying in math. Did we change the value? No. If I type in the square root of 25 on a calculator, it's going to say 5.0. Same thing as 5, right? So we haven't changed the value, we've just changed the way it looks. We write it in a form that looks simpler, okay? So, yeah, that's rational, okay? Because we can rewrite it as 5. What about 33/9? Rational or irrational? And this is kind of a giveaway. It's pretty obviously one or the other. Which one is it? Why don't everybody type it in your chat so I can just see that you're following along here. 33/9. Is that rational or irrational? Okay, good. I'm seeing some answers. Okay. Okay, good. Looks like you got a lot of rationals. That's right. Well, it's rational because it fits the definition, doesn't it? It's written as a fraction. Can we go any further with that? Yeah, we could. We could simplify this a little bit. 33/9, 3 divides into both of those, doesn't it? So I could divide 3 into 33 11 times, and it divides into 9 3 times, and so I end up with 11/3, right? And if I type that in my calculator, I get 3.6 repeating. Okay? What about the next one? Square root of 11. Rational or irrational? Type it in. Square root of 11. Good, good, good. Okay, good. Seeing lots of irrationals. Good. That's correct. Square root of 11 is irrational because it's not like the square root of 25. The square root of 11 does not simplify to an integer. What's the difference? Well, 25 is what we call a perfect square. Whenever you take the square root of a number that is a perfect square, and what's a perfect square? It's just a number squared. Then you always get a rational result. But the square root of 11, we're stuck. That's not going to simplify. We'll review all that stuff in the near future, how we simplify radicals. But for now, we just know that it's irrational. If I put it in a calculator, it's going to be some crazy decimal that never repeats and never terminates. Okay, 17/34. We'll speed this up a little bit. 17/34. I could simplify that to 1/2, which is just 0.5. And then finally, what about this last one? That's a little bit tricky. Look at E. Is E rational or irrational? And keep in mind that rational numbers as decimals either repeat or terminate, and irrational decimals never repeat and never terminate. What's the verdict on that one? Okay. Irrational. You're right. It's irrational. That's a lot of people. That's a tricky one. A lot of times people get suckered in on this one because there is a pattern there, isn't there? The pattern seems to be like every time I have a 0, then I'm just going to increase the number of 3s by 1. So you could tell me what the pattern is. I would write down a 0, and then I'd have 5 3s, and then a 0 and 6 3s, and so on. So there is a pattern, but it's not a repeating pattern, is it? So that is definitely irrational. Okay? All right, so let's get to our notes then. Let's just summarize this stuff in our notes. So this is, everyone should have out that handout that I gave you. So the subsets of rational numbers, we know what these are. We've got the integers, the whole numbers, and the natural numbers. Okay, now let's organize these things. Let's organize these in a diagram. Now we call this a Venn diagram. This is a really important thing in math, a Venn diagram or a set diagram. We're going to represent the sets in this case as shapes. So we're going to say that the set of real numbers, all the numbers that you've ever used, it's an infinite set, but we're going to enclose all those numbers in this red box, this red rectangle. That includes all possible numbers of any kind. So then how would we represent the subsets? Well, there are two subsets, remember, of rational numbers. We've got of real numbers. We've got the rationals and the irrationals, right? Okay, so let's go to our Venn diagram. Well then, this biggest bubble, the biggest blue bubble that sits inside of the red box, that's what we would call the set of rational numbers, right? Q in this case stands for rational numbers. So that's all the possible rational numbers, everything that can be written as a fraction, okay? That's a subset of the set of real numbers because there are some real numbers that are not rational, but all rational numbers are real. Okay, what would the next subset be? Well, we could take a smaller piece of those rational numbers. All of the rational numbers that could be written with a 1 on the bottom are the integers, right? So we could call that subset I, which stands for integers. Inside that is a little bit smaller subset. This is the one that includes everything except the negative integers, and that would be the whole numbers, W. And then inside that, we've got only the positive integers, which is the set of natural numbers. Right, so this is how it's kind of, we call this a nested arrangement of sets. These are nested subsets. The smallest one sits inside the next biggest one, which is inside the next biggest one, which is inside the next biggest one, and they're all inside of the box of real numbers. Okay, so we took care of the rational numbers and all of the subsets, but then what are all the other numbers left over? So everything in the red box now that's not included in the blue bubble, the big blue bubble of integers, or of rational numbers, would be the irrational numbers. So the irrational numbers, in this case, they call them Q prime. That little symbol right there, that little dash mark is called a prime. So that's the set of irrational numbers. Now in our notes, they do it just slightly differently, and that's okay. Different textbooks use different values. Oh, real quick, here are just some other representations. You could do this in different ways. I don't want to confuse you. That one's just fine. But here's another way of looking at rationals versus irrationals. You can look at these if you want to. They're just slightly different representations, but they say the same thing. And then here's one I included just because not only does it include the real numbers, it includes all these other bizarre numbers we're going to talk about later in the year, these imaginary numbers. That one probably looks scary, though. Don't worry about it. We'll come back to that one later. Okay, so let's fill in some stuff for our notes. So the set of, do one thing here real quick. Where is that? Let's fill in some blanks here. So real numbers. In our notes, we're going to write real numbers as a capital R. That stands for real numbers. Real numbers are broken down into these subsets we've talked about, the irrational numbers and the rational numbers that can get broken down further. Okay, let's assign symbols to all those. Well, the irrational numbers, the real numbers we call R, we're going to call the irrational numbers. We're going to do this just a little bit different. In our notes, instead of using a Q prime, we use a capital I for the irrational numbers. We use a Q for the rational numbers. The integers we're going to call capital Z. The whole numbers we call capital W, and the natural numbers we call capital N. So just slightly different than the last example. Examples, irrational numbers, remember those are all the things that can't be written as a fraction. So things like pi, the square root of 2, the square root of 24, stuff like that. Okay. As decimals, they would be things like 3.14159, and on and on and on. Rational numbers, those are things that can be written as fractions. So 1/2, 2/3, -4, 0.5, 0.3 repeating would be some examples, right? Integers, remind me, what are integers again? Integers are rational numbers that can be written how? What's special about integers? Okay, good. Ones on the bottom of the fraction. Very good. Okay. So those would be things like -7, 3, 0, 111. And if we look at those as a set, remember the integers, they go forever in the negative direction, they count down forever in the negative direction, and they count up forever in the positive direction. Okay. Whole numbers, remember, they start at 0, and they just count up from there. Natural numbers are the counting numbers. They're just the positive integers. They start at 1, and they count up from there. So where would these go then? What do I call the whole box? If I'm going to make a Venn diagram to represent these sets, what am I calling the box? Go ahead and click your mic on somebody. I'm standing at the board. Help me out here. Real numbers. So we called those an R, right? Set of real numbers. On the last page, I guess. What's this little subset down here going to be, do you think? The set of real numbers. Real numbers is broken up into 2 different subsets, right? What's this one going to be? Or maybe we'll start with this one. What's this big subset going to be here? Q. Good. All the rational numbers. Very good. Okay, well then, what's the biggest subset of rational numbers? Integers. All the rational numbers with 1s on the bottom. And then a smaller part of that would be the whole numbers. And a smaller part of that would be the natural numbers, right? Natural numbers would just be 1, 2, 3, etc. The whole numbers would add 0 to the picture. The integers would add the negative values, the negative whole numbers. And then the rational numbers would add some other things that aren't integers, like 1/2, negative 2/3. What's left over here then? If these are the rational numbers, what must this other little set that's different be? Irrational numbers. Good. So square root of 2, pi, etc. Okay, good. All right, so, and I'll put these up. I just put this in here to remind you about this. If you miss the lecture, I will always put up a filled out version of the notes too. So you always have access to this as well. This will be on the Google Classroom stuff. How are we doing for time? Oh, are we done? We're done. We're a minute over. Do that e-ticket. It's real short. I think it's only 4 problems. That's due tomorrow. If you have any issues at all, come see me during office hours today. And it's lunchtime. Any questions? All right. Well, I'm glad to have you back. I know summer's great, but I'm ready to do some teaching, and hopefully you're ready to do some learning. So I'll see you in a couple days if I don't see you at office hours. All right. Have a great day, you guys.